Well, welcome back. Nice, delightful Friday morning out there. Nice, wonderful weather. It's almost spring, it feels like. So, the elimination tree. Remember, the whole goal of this process here is we're trying to get a grapple on what is the non-zero pattern of L. Okay, so that governs how we can then do the numerical calculation. Where are the data dependencies? What depends on what? How can we lay out the numerical computation to make it as fast as possible? And a lot of that depends on the elimination tree. The tree, if you remember, we started with this the Oliver Twist here of the story, of the book, right? The graph of L for the sparse triangular solve, we saw how that created a lot of neat combinatorics. And then when L is symmetric to Cholesky, we can prune this graph. We realize, hey, we don't need this whole graph of L. We can get the same answer with a terser graph. And it becomes a tree. Now it's really easy to search a tree. All right. So this tree is essential, although what's interesting about the tree, historically speaking, is that people did these sparse matrix computations before they knew about the elimination tree. And then as they were doing the computations and thinking about the combinatorics and how the pattern is related, what relationships are there in the pattern, they realized, oh wow, there's this object underneath called this elimination tree that's governing a lot of the things we're trying to do. And if we know this tree, it really simplifies things. So let's compute the tree, and let's compute the tree beforehand, because obviously if you have the matrix L, all you got to do is look down each column and find the first non-zero entry in every column, and that's the parent. If this is column I and this is J, and you go down, well then I is the child of J. All right. So, but we don't want to do that. So last class I showed you the theory behind computing the tree, which is based on this notion here that says that if there's a non-zero LKI, okay, from K to I in the graph, then there'll be a path from I to J in the elimination tree. So this edge right here is not in the tree necessarily. It might be the trivial case that I is a child of K in the tree. But if there's an edge from I to K in the graph of L, then there's a path in the tree from I to K. And then this theorem changes as well, becomes more specific when we realize that the tree is fully characterized by this theorem, by these row subtrees, and finally, when you realize what the row subtrees mean, the fact that hey, that really captures the non-zero pattern of a given row, then the elimination tree is driven by this computation is driven by this theorem. If AKI is non-zero, then and it's below the diagonal, K is greater than I, then I is a descendant of K in the tree. And if I is a descendant of K in the tree, if we have constructed a tree so far to step K minus 1, and we have K here, we're trying to figure out, well, who's your children? I come from Indiana. See, I'm a Hoosier, so I can ask this question. Who's your children? You walk up K, you walk up the tree, and you come to an ancestor here, and you get stuck. And if you get stuck with this theorem, well, wait, it says this theorem says there has to be a path from I to K. And you've gone here and you've gone as far as you can, so this must mean there's an edge here. So now that node here, I forget what I call this in the code. I don't think I give it a name. Must be the parent. K must be the parent of that last known ancestor. So that gives us this algorithm here, and we briefly looked at this. So let me look over this in more detail. There's this extra parameter to this function called ATA. And we're going to use that later. This, so far, is we're constructing the elimination tree of the matrix A. But later on, we're going to need something different. We're going to need also to construct the elimination tree of the matrix A transpose times A. And ATA is a matrix that governs sparse LU factorization and sparse Cholesky sparse QR factorization. So we haven't gotten there yet. So you don't really see yet why ATA is important. So let ATA be false. It's a flag that just says, are you doing A or are you doing A transpose times A? So for now, I mean, it didn't make much sense to write two versions of this code. Although, except maybe to put on the slide, I should have made a separate version to just pull this parameter out. But if AT is true, you need extra workspace, and you need this previous flag. So forget that right there. And forget if ATA, so this is false, ignore that. And I'll explain where those come from when we get there. So we start off, in fact, the parent array is simply an uninitialized space. It's not just a forest of n nodes. It's not actually, we don't actually need to define it. So we start off implicitly with a tree that looks like this, but in fact it's not even defined, but implicitly that's what it is. The reason I don't need to define it is because at the kth step, so this is node k, at the kth step, the tree here for nodes 1 through k minus 1 is fully defined, and all I need to do is define the parent of k and then set the parent of k to be null. So that's all I need to do, and null means, in this case, -1, because I'm using the numbers 0 through n minus 1 to denote a node in the graph. So I need a number that says there is no such node, and that's -1. So at the very end of the computation, the root of the tree will have no parent. So parent of n minus 1 will always be -1. That just denotes that it's a root. So when we come to this new node k, we want to tack on. We have the graph so far, the tree so far. We're going to tack on this graph. So this node at the top. So where to put it? We've got some subtrees here, and which of these are children of k? Some of them will be, or maybe none of them, possibly, if k is a leaf. The first thing we need to do is define k to have no parent and no ancestor. If you will, and if it has no ancestor, that's an important fact, okay? Because it says it's a node that has no ancestor is then known to be the root of its subtree. So the ancestor of this node right here will be -1 because it's not yet been given an ancestor or a parent. And we'll need to know that because we need to know when we come to a point and stop. So if we're in this subtree here, we started a node I, and we walk up to the root of this subtree and stop, we need to know where to stop. And the point at which we stop is a point at which we have no parent and no ancestor. Okay, so you initialize that node k now to have no parent and to have no ancestor. Now we need to walk across every non-zero in this column of A. So what we're doing actually is walking across the row of L. So we're going through equivalently, this is the leading k minus 1 part. So we're doing essentially the triangular solve. We're taking all these non-zeros in A, and we're using them now to say, well, we're trying to determine this row, but we don't want to walk across this entire row of L. But what we're trying to do is get a grip on the row, the TK, the T sup K row subtree. So that the kth row subtree is actually a true tree. I wish we called it the elimination forest, not the elimination tree. Because this T sup K is actually a tree with the root of K. And it's a subtree. It may have descendants down here which are not in the tree, but it's governed by nodes. See, all these nodes that are this tree is defined by its leaves. Each of the leaves are non-zeros in. So are non-zeros in the matrix A. So if AKI is non-zero, node I is one of these leaves. Well, node I may be here. So there's a special case that it's a leaf, but any leaf will be a non-zero in A. There will be some non-zeros in A which are not leaves. So what we want to do then is we want to look at each of these non-zeros in A and follow up to TK. But what we're going to do, since it's not constructed yet, we're going to have to we'll end up stopping early at some point. So we'll have some subtrees in the elimination tree. This one, say, and this one. We'll stop early. We'll wait. If we know what we have, we know that TK is actually a tree. So if we stop early, that must be the parent. And I also showed you the theorem for why that's true. Eventually, you'll reach the parent. As you walk from I to K, you must reach the parent. So let's walk up the tree. So we start with a node I, and so ATA is false. So we just get A of I, AI of P. So we get a non-zero here in the A matrix. We get one of these 5 nodes, 1, 2, 3, 4, 5, and we're going to start walking up the tree. But we've walked this path before. So we're not going to walk parent to parent to parent to parent. We're going to jump up as far as we can to an ancestor. So rather than walking up from the parent to the parent to the parent, we'll walk up to the ancestors. This could just easily be changed to I next equals parent of I, and the code would work. It'd just be slower. So this is just a shortcut. And so is this. This is just a shortcut. We could leave this out. We could take these 2 lines of code out and say, well, just I next is parent of I. And if the parent, so if you want to understand this code in a way, you can say, well, forget this ancestor nonsense. Just delete these 2 lines and change this to, say, I next is parent of I. So you're just walking up the tree. It'll work just fine. In fact, if you want to play with the code, take those 2 lines out and put in that statement that I next is parent of I, and just watch it work. It'll work. It'll just be a little slower, asymptotically slower. So this is walking up the tree. It's starting off with I, and then it's going to continue iterating until it sees a node that doesn't exist, or until it stops before K. It'll stop there, and it'll then walk up I next to the tree. If it comes to a node, though, if it comes to a node that has no ancestor, that node also has no parent. And so it sets the parent of that node to K. The ancestor idea does the following. It says that, well, if I walk this path again, my goal is to reach the root of this subtree that I've built so far. So I don't want to have to walk this path all over and over again. I'd like to just jump straight to K. So ideally, as we walk this path, it'd be kind of nice if we could say, well, all of these nodes along the path should point directly to K. They should all be updated. They should all know their ancestor. Everyone needs to know who is the representative of their subtree. We've got this elimination tree that's partially constructed, that we're doing the set union on. And we're saying, well, if I have a node here and I have a node here and I have K, well, then I want to take the set union of these two disjoint sets. And so everyone in this subtree ideally would know immediately in constant time who their ancestor is. It's now K, and it was this node before. But that's too expensive to update. And so rather than updating it so extremely, we say, well, we're going to take shortcuts. So suppose I took a shortcut from here to here. And suppose I took a shortcut from here to here, and then this one was no shortcut. So suppose this is the ancestral link. It's not going up parent, 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 but it's going, grandfather, grandfather, and happens to go to parent. Well, I'm not even going to touch this node. This node may think that this is my ancestor. So the shortcut is just slowed down a little bit. That's okay. I'm going to leave that alone. But I can update this guy. I can tell, look, I'm walking through these nodes, and I know when I'm done, I don't know where I'm going to reach K, but I know I have a distant ancestor K up there somewhere. I'm going to reach it. I'm going to, walking the yellow brick road, I'm going to come to Oz. Okay, I'm going to hit this node. And so as you're walking this path, the ancestral path, you can change. It sounds like something out of Zen Buddhism. Walk the ancestral path. Something Luke Skywalker would say. That is probably a lot of Buddhist theology in that movie anyway. I think it's Buddhist. I don't know. So we're walking up this path, okay, and we're just going to update this ancestor to K as we go along. And finally we hit the end and we realize, okay, there we're done. And so all these nodes now point ancestrally up to K. And if the next time around we come to this node, well, we'll eventually reach K. We'll just say we'll go here, we'll go here, and then we'll go here, and then so the ancestral information might be stale, but it still works. You'll still get there. You just might take a few more hops than you might hoped. And so that's why this algorithm does not take linear time, but it takes quite close to linear time.
So if you happen to, instead of, you had an example where you said, okay, if we hit the parent of I, it'll take a couple steps. If you happen to hit the grandparent of I, then it's pretty much no steps. Is that?
Well, if you hit the grandparent, you may be 10 generations away.
Yeah.
So you may have several hops to make.
Well, what I'm saying is if you do I, and you follow that example that you have, and then on the next loop, the next iteration of the P loop there, you hit the grandparent of I. Right. Now its ancestor is already K, exactly. So you're already done.
You're done.
Okay,
right.
I got it.
Exactly. Yeah, this ancestral information gets updated a lot. So yeah, if suppose you were here. Okay, suppose for example, so the comment Ed made was that, well, suppose you do this node first, and you walk up the tree, and you come across this node by chance. Maybe he thought his ancestor was here, and then he's done. But then if you come to this node again, the same step of the algorithm, you've already updated the ancestor to K, and you're there. Yeah. So yeah, it's updating, it's doing its updates for not just the next iteration for K, but it's also the next I even. Yeah, is going to be affected by this ancestral update. That's it. That's that simple. It's the number of papers have been written about this very algorithm is probably equal to the number of lines of code in this. I kid you not. Because, there was yet another paper that was written on that turning an ATA flag to true. It was another paper. Well, I think there was a little bit more to that paper than that observation as to how to construct the tree of A transpose A. There's a little more to it than that, but that was a good part of the paper, was how to construct the tree of A transpose A without forming A transpose A explicitly. And it's a pretty cool theorems and observations that leads to just a trivial amount of code. That's what's amazing about this. This chapter has the thickest amount of theory per lines of code as any I've ever seen in algorithms. There are a few other things that are like that in algorithms. Things like the disjoint set union find algorithm. A lot of theory behind it. Very, very subtle. But you see, that's what this is doing. It's a disjoint set union find algorithm. Okay. To do this in optimal asymptotic time, there's another thing that would need to happen here, and it's called path balancing. The idea is that you walk, and you've created this path. All these paths decay, but then what you need to do next is go back over it again and somehow balance. I forget the algorithm, but there's a balancing, and you don't necessarily make k the ancestor. You want to try to keep the paths equally short. So there's a theory behind how you do that, and that's where you get this inverse Ackermann function. If you do it this way, you get this this has a logarithmic time complexity. So it's the time complexity of the algorithm is the number of non-zeros in A times the log of the number of non-zeros in A, which is bounded by n squared. So it's A log n. So this, even though it's simple, it's simple and taking all these nice shortcuts, and it works well in practice. It does have this extra logarithmic factor. The thing of it is, though, that logarithmic factor is never observed in practice. It's a very loose upper bound, that log factor. You can construct a case for which that'll occur, but it just doesn't occur in practice. In fact, can you construct? I'm not sure if you can construct a matrix. You can construct a chain of possible events. I'm not even sure there's a matrix that exhibits that logarithmic characterization. That'd be an interesting project to try and figure out if you could force this algorithm to take logarithmic n log n time, for instance. And there might be some even deeper theory that says why that's the case. But I don't know what that theory is. I don't know if anybody has dug that deep yet. So this gives us then a method for doing a sparse triangular solve. Okay. What we had. So if we go back, let's see. I'll have to go back to chapter 3, but I won't do that. I guess I already talked about this algorithm, didn't I? Yeah, I did. I jumped ahead, talked about it, and came back. So now that we have the tree, now it's very easy to actually construct the non-zero pattern of each row. So the tree's built, and all we want to do is we're at a row k, and we want to find the kth row subtree. This right here, the kth row subtree. Then all the nodes in the kth row subtree correspond to non-zeros in the kth row of L. So to find that, we took these shortcuts to find the tree, but now if I actually want to enumerate all the nodes in this tree, I cannot take the shortcuts. I actually have to traverse the whole path. And that's what this code does. So it starts at the leaves, or it starts at a row, a node I, where AKI is non-zero, right here. And it just walks up the tree until it finds a marked node. And the cool thing about this loop here is that we know now that we're going to terminate at node K, because we know that the root of the kth row subtree is K. It's a tree, and its root is K. If we mark node K, then we know if we traverse up that path, we will find K. And so thus we will find a marked node, so this will terminate at least at node K, if not before. It can't go further. It will see node K. So then all you have to do is walk up the tree. When you see a node, as you see that our nodes are not marked, and then add it to a list, mark the nodes. And then when you walk up the tree, we need to make sure that this list is put into topological order. And that's what this while loop does. Now, if you didn't care about the topological order, If you just said, well, what's the non-zero pattern of the kth row of L in any order? I don't care what it is. Then you wouldn't need this. You would just keep incrementing length. Say you'd put it at the front of an array S or something. You'd keep incrementing it, and you wouldn't decrement it down to 0 here. Delete this. In other words, if you were to delete this line of code, then the list of entries would just be stuck to the front of this S array, and you'd have to change this loop to iterate instead of top to n and go from 0 to length to unmark the nodes. This turns the nodes, it turns the marks on the nodes off because we want to clean that up when we're done. This is just, these two lines of code are just cleanup. So we can use this array W again for another pass of this algorithm. Then you can just delete this line of code. It's not necessary if that's the case. But if we do want it in topological order, we've got to traverse the path and then stick it on a stack backwards in the opposite order that it's been traversed. And that's what this does. And that's it. So what this is doing then, it's giving us this answer to this question. What is the non-zero pattern of L/B, L backslash B, when L comes from a Cholesky factorization? What's the non-zero pattern of that answer? And it's also giving the non-zero pattern of the kth row of L because the triangular solve can be used to compute that kth row of L. So, very simple, very elegant algorithm. And the time complexity of this one now, there's no funny inverse Ackermann function here. If you look at this carefully, you realize that, hey, this is taking exactly time proportional to the length of that list, which is the number of non-zeros in the answer, number of entries in the answer. This loop is not a concern here. You might think, well, wait a minute, I've got two loops that are nested. Couldn't that, multiply the time complexity? It can't, because every non-zero in A is also a non-zero in the result. Because the non-zero pattern of A is a subset of the answer, so we don't have to worry about that. So the time complexity is just that we can hide that. It's the time complexity of this plus this, if you will. So for every one of these, we're incrementing at least once there, and at most once. Well, no, not at most once. What am I trying to say? This statement here will execute once per non-zero in the result. That's clear. This loop here, the same thing. We'll iterate that many of times. So that's clear. These two. So the time complexity of these two lines are taken care of. There's extra work here, though, that takes time proportional to the number of non-zeros in A. These four lines here. This line here might take unit work when it does no work inside the loop. So then how do you account for that? Well, you account for that for the fact that these three loops here iterate this many times, and this is the number of non-zeros in that kth row of A. So the total time complexity then is number of non-zeros in the kth row of A plus the number of non-zeros in the kth row of L. But the number of non-zeros in the kth row of A is less than the number of non-zeros in the kth row of L, strictly less than or equal to, because it's a subset. So that's where the total time complexity comes into play. So that gives us the triangular solve. And then once we have the triangular solve, we could use this, but I don't here. We could use this all the way back. Well, I don't have chapter 3 notes, but there's that SP solve function, right, that does the graph traversal and then does the numerical solve. Well, there's the graph traversal. We could replace it with that. So now we've got this tree, we've got what else do we need, right? We've got the tree, we can find the kth row of L, and what else do we need, right? Well, we're not done yet. The reason we're not done is because to do this numerical calculation efficiently, I'd like to know more than just the tree. So I know how to form the tree in time, more or less, order, non-zeros, and A. Almost linear time. Great. Then I could use this algorithm here to build the whole matrix. Okay. But if I do that, there's several problems with that. First, I'm building it row by row. What if I want to store it column by column? I could transpose it, There's all this stuff that, wouldn't it be... It'd be nicer if we could do some more combinatorics here to figure more stuff out before we start spending order L time. So I want to postpone this amount of work as much as possible. I want to find out as much as I can about the matrix L before I want to take time of this. And certainly before I want to take memory of this. Because what if I want to do this in a distributed computation, for example, in parallel? I might not have that amount of memory on any one node of my machine. Okay, so I want to keep this analysis as concise as possible. One thing that we'd like to know then, as we're doing this analysis, to map out the numerical computations most efficiently, I'd like to know two things. I'd like to know the number of non-zeros in each row and each column of L. So how many non-zeros are there in this row? And how many non-zeros are there in this column? Those two questions. And if I know that, that'll be really useful. Why would it be useful? What about the columns? Well, the columns are useful because what if my matrix on output is going to be stored by column by column? Then I need to know the column counts so that I can compute the column pointers. I can do the cumulative sum of that, and I can map out my data structure before I build it, before I create it. I just say, this is how big it's going to be, this is how big each column is going to be, then I just fill it with numerical values, compute it, and I'm done. If I use this algorithm here, I would end up computing the pattern row by row in topological order, not sorted order. Maybe what if I want to sort it? Well, then I have to do a transpose, double transpose maybe. Okay. And it takes time order L to know how big to make that data structure in the first place. See, if I just started with this and said, let's use this to create L, well, how big is L going to be? I don't know. I have to do this work first. So I have a dynamic memory allocation going on. It's not pretty. And if things are dynamic, that means it's also difficult to do in parallel or to do with high-performance methods that need to know these are called supernodal and multifrontal methods. They need to know where are the cliques in the graph, where are the big dense substructures that I can exploit and really operate on quickly using dense matrix operations, where the cache is really friendly to me. To answer those questions, I need to know more about this matrix L other than this kind of information. And one of the things I need is the counts, the row and column counts. And all this, by the way, can be done in MATLAB in one statement. There's a MATLAB function called SIMBFACT. It's a funny name. It sounds like something you might find on a Wikipedia page about the Lion King, right? Facts about Simba or something. I don't know. It's just pronouncing it is weird. I would have left this little B out if I were to call it SimFact. You can say that, but SimbaFact. You gotta put a B in there, and it sounds like Simba Fact. Wasn't Simba the little lion, right, in the Lion King? Yeah. So the Simba Fact in MATLAB will do all this for you. And trying to remember if I wrote SimFact in MATLAB. I can't even remember. It's in there, but I don't know if they use mine or somebody else's. I used to know the answer to that question. You know you're getting old when you can't remember. You look at a piece of code. Did I write that? I can't remember. I'm getting old. Man, oh man. Okay, so the row and column counts. The column counts are really tricky. So let's not do those yet. We will. Let's just look at the row counts. What are the row counts? The row counts is just the number of nodes in this tree. The number of nodes in this tree is to find the number of nodes in the tree without traversing all the nodes. Imagine that. I've got a subtree of the elimination tree. Okay, here's T sub K. This over here, camera. Thank you. Yeah, there we go. I've got this tree. And I want to find the number of nodes in this tree. I can traverse all the nodes one at a time if that's the algorithm right there. I don't want to do that. I want to find the number of nodes in the tree without actually walking every node. And to do that is going to take some work. Let's see. To do that is going to take lots of notions. Let me jump ahead and I'll show you the kind of notions we need. We're going to require ways of quickly finding a least common ancestor. Okay. Let's suppose I have a really cool and efficient way of asking, given a node here and a node here, who's your least common ancestor? Just pretend I had that. And given this node and this node, so pairs of nodes, these two nodes, their least common ancestor is here. That's where those paths collide. And these two nodes, what if between these two nodes I could magically find the least common ancestor, that box? And between these nodes, suppose I could magically find in constant time their least common ancestor, or near constant time. So those are those four pairs of nodes, 1, 2, 3, and 4 least common ancestors. Then what I want to do is I would need to know these least common ancestors then can break the path up into subpaths, break the tree up, into subpaths. So we'll have some magic to find these least common ancestors efficiently. And then between these pairs of nodes, walking from left to right, which implies then a post-ordering. Right? So there's going to be first a post-order of this tree to lay it out, if you will, left to right. And then I'll walk across the tree left to right in this order. And I'll say, let's see, I want to make sure I do this in the right order. I can use path decomposition to break this path into into disjoint subpaths. This is called path decomposition. And so there would be the first path. The first child goes all the way to the parent, but nobody else goes to the parent. Just the oldest son here knows the parent. And sorry, these guys will not reach the parent, the root. Sorry. Okay. Then when I go to this node, I'm going to walk upward. Well, I'm not going to walk the path, but the path is going to be defined this way. It's going to be defined to the least common ancestor of the node before me on this list. So nodes 1, 2, 3, and 4, and 5 are all the leaves of the tree. I need to know where the leaves of the tree are, too. Because if I have a node here up in the middle of the tree, I don't want to consider that node. So I only want to work on the leaves. Remember this picture here I drew, I had 4 leaves but 5 non-zeros in A because I had an extra one there. Well, maybe I got an extra one here. I want to ignore those. I only want to look at the leaves of this tree. And between 1 and 2 then, I stop at the least common ancestor of 1 and 2. Then I go to node 3, and I want to think of the path that goes from 3 to the least common ancestor of 2 and 3. So think of that path. And now between 3 and 4, I want to think of another path. I'm not going to traverse this path, but this is the path 4 up to just before, if you will, the least common ancestor of 3 and 4, which is now this path. And now think of the last path between 4 and 5. I want to go from 5 up to, but not including, the least common ancestor of 5. So I've got 5 leaves. I have 5 paths that are all disjoint. They do not overlap each other at all. So the kth row subtree now has been broken apart just combinatorially. We're not going to compute. We're not going to walk these paths. Okay, we're just thinking about the structure of this computation. The structure of what it is we're doing is called path decomposition. The tree has broken now into 5 paths because I've got 5 leaves, and they do not overlap at all. Okay. The number of non-zeros in this row of the matrix is equal to the number of nodes in this tree, the kth row subtree. And so that's the whole goal. I'm trying to count, well, how many nodes do I have in this tree? That's the end goal. Count the number of nodes in the tree in time proportional far less than the number of nodes in the tree. So I can't go node, 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 node. I could do that with that algorithm right there, or with the one before. I don't want to do that. So to do that, we need the least common ancestor. The least common ancestor, then we need a post ordering. Then we'll find least common ancestor between pairs of nodes adjacent in that post order, from left to right. And now that breaks the tree into subpaths. Well, if I knew how long each subpath was, I could just sum up from 1 to 5 all the lengths of each of these subpaths. And that would be my answer. How many nodes are in the tree? Well, if this path is a length 10, well, there's 10 nodes there. And if this is a length 5, if this is length 10, and this is length 5, and this is length 7 and 12 and 2, well, then if I add up these numbers, 10 and 5 and 7 and 12 and 2, that's my answer. Well, that sounds like a tall order. Well, finding the length of a path is easy if we know the level of each node in the tree. If I have a path defined by its start and its finish, then if I know that in the grand tree, capital T, okay, T period, which I've computed the tree. If I knew the level of each node in the tree, so I've got this whole huge tree. Now, the kth row subtree is just a piece of that. But if on the entire tree, I know that, okay, this is at level, I forget how it's defined, 0, and this is at level 1, and then 2, and then this is level 27. Okay. Then if I say, well, hey, I've got a path that goes from node 27 to node 2. I'm sorry, this is a node level number. Suppose this is node 1, and this is node 42. And node 1 is at level 27, way down in the basement. It's a leaf. I don't know why computer scientists like to draw trees upside down. It's like, wait, the leaves are supposed to be, and they call this the root. It's like, wait, the roots. This is the dirt, right? The roots are supposed to be. I don't know. We're dyslexic. Isn't that cool? Okay. So if I have node 1 and I have node 42, and I know there's a path between them, I can say, well, the path length is just the difference of the levels without traversing the path. So that's what's going to be used to find out this number 10 here, that there are 10 nodes here, because I'll know the levels. Now, but how do you find the levels? Don't you have to traverse the whole tree to find that? Well, yes, you do. But we're amortizing this cost over and over again. If you've computed the tree already, I've shown you how to do that in time proportion to the number of non-zeros in A. Well, then it's also then very easy, actually, in order n time, to find the level of every node in the tree. Just do a traversal of this tree once. Mark every node with the level. Go from the top down and just mark all the nodes. It's in time linear to the size of the problem, which is n. Okay, now once I'm at a particular row, I'm not going to spend order n time. N is big. Okay? But n is amortized across the whole computation of all the row subtrees, of all the counts. So n is not a problem. N does not dominate our time. So finding levels is easy. Just a standard algorithm to pre-compute it for all the k row subtrees, 1 through n. And then I need to know, well, first descendant is going to be used to help me know what the skeleton matrix is. The skeleton matrix is this other notion that says, well, if I'm going to do this process, if I'm going to slice and dice up the tree into these 5 paths, then I have to be able to ignore these other nodes along the way, which, suppose I have 5 leaves of this kth row subtree, but I have 8 non-zeros in the kth row of A. So I have 8 fingers. I mean, think of the graph traversal. You put your 8, you're doing a triangular solve, and you want to know what's the reach of my 8 fingers. And you walk the graph, and you realize that, oh, wait a minute, these 3 I could have ignored. Because if I start from these 5, I will see these 3. I joke with my kids, how many fingers do I have? And they tell me, 8. I only could do this once. No, I have 10 fingers, but I'm only showing you 8. Okay, so how many leaves are there of the tree? Well, there are 5 leaves of the tree, because you'll start with these 5. You'll see the other 3, so you really only had the 5. You only really had to consider the 5. And you don't want to consider the 3, because if you did, you've got extra paths. You don't want to do that. These 5 have a special name. The 3 we throw away are entries in the A matrix that we're ignoring. We're ignoring because we're not just ignoring arbitrary entries. We're ignoring them because they're not leaves of the tree here. The 5 of the 8, those 5 entries are entries in what's called the skeleton matrix. The skeleton matrix is a matrix. So you have this matrix A. Do the Cholesky factorization, you get L. Okay. If for the moment we forget the non-zero values, which we're doing already now for a long time, it's like, wait, we're supposed to be doing numerical computations, right? We haven't talked about numbers, floating point numbers, for days now. Yeah, we'll get there. The skeleton matrix says you have a matrix A, and here's your L. Well, if you start throwing entries away selectively, but you still, because of fill-in, you still get the same matrix L, and you do this as much as possible. You throw as much away as you can, but still get the same output matrix L in terms of its pattern, then that's now called the skeleton matrix. It's the bare bones matrix, and it's 920. So those are the 5 notions that we're going to use in the whole rest of this chapter 4 to create. We're going to do post-ordering of the tree. We're going to find then the least common ancestors, use path decomposition, first descendants level, skeleton matrix. All that just to answer this question. We'll do that Monday, starting Monday. See you then.